This lecture series introduces you to organic reactions, their general mechanisms, and energy diagrams. First, we'll start by looking at 4 classes of organic reactions shown here. And these categories are determined by how many reactants convert into how many products over the course of the reaction. In the first, addition reactions, 2 reactants combine to form a single product. And in a simplified or general form, we depict that as A plus B goes to C, or 2 reactants, A and B, combine to form a single product, C. In the second category, an elimination reaction, a single reactant, A, splits into 2 products, B and C. In the third, a substitution reaction, 2 reactants, here A and B, exchange parts to generate 2 new products, C and D. Finally, in a rearrangement reaction, a single reactant, A, undergoes rearrangement of bonds to form a single isomeric product, B. And we'll see these classes of reactions in more detail and with some examples in the next video. These classes of reactions are a way to categorize the changes happening during a reaction, but they don't tell us anything about how the change or the reaction is occurring. And that's the role of the reaction mechanism. The mechanism of a reaction is a description of how a reaction occurs. It tells us which bonds are broken and formed and in what order. And here we have 2 different ways we can break bonds, homolytically and heterolytically. And remember that in each bond there's 2 electrons. And the 2 mechanisms for bond breaking differ in where those 2 electrons go when the bond is broken. In a homolytic bond cleavage or breaking, one of the bonding electrons stays with each half of the molecule. And these are called radical reactions. As we saw with acid-base reactions, we use curved arrows to indicate the flow of electrons during a reaction. And for a homolytic bond cleavage reaction, where the 2 electrons in the bond go to different places, we use single-headed arrows. These arrows, with only one hook on the end, here, a single-headed arrow indicates the movement of 1 electron. Alternatively, the 2 electrons in the bond can move together to one of the atoms. This is called a heterolytic bond cleavage. And these are polar reactions like our acid-base reactions because the movement of electrons to one atom of the bond over the other occurs for polarized molecules or bonds. And for these reactions where both electrons move together, we use double-headed arrows. And a double-headed arrow has 2 hooks at the end of the arrow, indicating the movement of 2 electrons. Let's take a closer look at radical reactions, reactions that proceed with the movement of single electrons. There are 3 types of reaction steps that make up a radical reaction. First is initiation, or radical formation. In this step, a non-radical species undergoes homolytic bond cleavage to form 2 new radicals. This type of step is often initiated with light, or UV light. So if you see light over the arrow, there's a good chance that you're looking at a radical reaction. Next are the propagation steps. And there are an array of different propagation steps that can occur for any given radical reaction. And that's because in a propagation step, a radical reacts with a non-radical to form a new radical species. And there are often many different ways that this can happen because there are several different radical species and non-radical species in the reaction mixture that can combine in this way. The radicals that are formed in these propagation steps continue on in the reaction, mostly into new propagation steps, but occasionally into a termination step. And in a termination step, 2 radicals combine to form a non-radical product. And although it's easy to think about this step as forming the main reaction products, the reaction products are most often formed in propagation steps. Okay, and here we've been looking only at the individual reaction steps that make up the overall reaction. The overall reaction that corresponds to these steps is the reaction of chlorine gas with methane to form chloromethane and HCl. And the overall reaction is shown at the top. And again, note that the indication of UV light suggests that this reaction will proceed through a radical pathway or mechanism. Okay, now let's take a closer look at polar reactions, the reactions that involve the heterolytic bond cleavage of polar compounds. And here we'll use a generic addition reaction of A plus B forms C. But in this case, I've drawn C as the molecule in which A and B are now bound together. And the two reaction partners behave differently in a polar reaction. One reactant is electron rich and attacks the other. That's A here, while the other is electron deficient and is attacked by the other reaction partner. That's B here. And the electron rich or nucleophilic reactant is called the nucleophile. This is the site of high electron density in the reaction. And the electron deficient or electrophilic reactant is called the electrophile. And this is the site of low electron density in the reaction. And in order to determine the mechanism of a polar reaction, we always start by identifying the nucleophile and electrophile, the nucleophilic and electrophilic sites in the reaction. So let's look at some common examples of nucleophiles and electrophiles. Nucleophiles are sites of high electron density. So these will be molecules with lone pairs and pi bonds. And if you see a negative charge, then that's also a site of high electron density. Common nucleophiles are nitrogen and oxygen atoms that bear lone pairs. And although alkanes are not good nucleophiles, alkyl metal reagents are. So here we have a carbon bound to a magnesium, a metal, and this metal carbon bond is super polarized towards the carbon, so much so that we can think of it as an anionic or negatively charged carbon and a cationic or positively charged metal. So these are very good nucleophiles. And finally, pi bonds or alkenes can also act as nucleophiles. And here the site of high electron density is the pi bond itself. So in these cases, the pi bond can participate in or initiate the reaction. Electrophiles are sites of low electron density. So these will be cationic or positively charged carbons, or structures that have a partial positive charge on carbon. And remember that the partial positive charge arises from a polar covalent bond. So alkyl halides with a polar carbon-bromine bond will have an electrophilic carbon. Carbonyl compounds with a polarized carbon-oxygen bond will have an electrophilic carbon. And structures like this one, an iminium, will be electrophilic at carbon because there's a resonance structure in which the positive charge resides on carbon. Okay, let's end this video with a concept check. Take a moment to classify the reactions shown. Okay, here we have two reactants combining to form one product. And so this is an addition reaction.